Oh, thank you. I'll be right back. Alright, it's not working. We've got room next door though, so can you all come? There should be enough room there. I can't get it to work. Okay, sorry. Yeah, can you go next? I can't get the link to work, so can you go next door? There should be enough room. No, you're right, you're right. Just, there is enough room, I think. Yeah, okay. All right, sorry for the delay. So if there's anyone next door, I can't get the linking to work, so come in here, please. Is anyone in there? Awesome. Right. Has anyone, did anyone say watch the recording of Monday or Tuesday's lecture this week? Yep. Is it working? Yeah. So me swapping the screens isn't doing anything to the recording, is it? Mondays is fine? Excellent. All right. Okay, so as I said, we're basically going to spend this week and next week looking at integration strategies. And as I explained, unlike differentiation, integration can't always be done. So I'm assuming everyone already knows the basics of integration and the integration technique, what I call integration by basic substitution. And by basic, I don't mean easy. By basic, I mean the substitution will hopefully be obvious from the question. Now, I had some examples in here. Now, I want to do some of them by hand just to show you some hints. Let's just talk about the first one. Unfortunately, with integration, I can't give you any hard and fast rules. You need to be able to look at the problem. Sometimes it's obvious. When we're finished next week, sometimes it's obvious what technique to use. For example, if it's a rational function, you try partial fractions, which we're going to cover next week. But a lot of the times, you look at it, you're not sure what to do. Always try a substitution first. Right? One hint I can give you, which also does not always, not a rule, it's a hint that works most of the time, is if there is a square root in there, you will do whatever it takes to get rid of it. All right? So what I mean by get rid of it is, this one, for example, has got the square root of 1 plus x squared. So the first thing to try is you let u equal 1 plus x squared and hope it works. Right? Because that'll just leave you u to the half. That we can integrate. Integral of x to the n is x to the n plus 1 on n plus 1 for all n except minus 1. One of the integration techniques we'll do next week is integration by inverse trig substitution. Probably the most powerful integration technique we have, and it is a technique designed solely to get rid of square roots. Right? That's its purpose, basically. Right? But we'll talk a bit more about that one next week. So the first one, we hope that u equals 1 plus x squared works. And when you get the hang of it, you'll see before you even get started that it's going to work. Because if I let u equal 1 plus x squared, the derivative of 1 plus x squared involves x, because it's 2x. And with any luck, fingers crossed, that x is going to cancel with the x out the front. Done. Right? Notice how I do it on the right. I write a little heading, change a variable. That's where I work everything out. Right? So my substitution for u that I'm going to try, find du dx, and then thinking of du on dx as a fraction, just like we do with the chain rule. Solve that for dx in terms of du and x, right? Just thinking of it as a fraction. Then I attack the integral and hope that it gives me something I can handle. Right? And of course, this one just becomes the integral of u to the half. Done. And just like with the chain rule, you throw out the u when you're done. So you must replace the u with what you started with and then add plus. Always add plus c. And as I explained in the last lecture, this isn't us being pedantic. There is a very important reason we have to add plus c when we do indefinite integrals. Once you get the hang of it, it becomes, by basic substitution we mean it's obvious. So this one, for example, the integral of 3x times cos of x squared, well, hopefully you can spot that it's basically something like f dash times cos of f, although I hate those rules, but you can think of it that way. Let u equal x squared, that should get rid of the x out the front. Notice I have a habit with integration of ripping out all the constants and putting them outside so I can just concentrate on the integral. The only catch is don't forget to keep bringing that constant along. Right? So the 3 on 2, I take it outside, end up with something the formula sheet helps me with. Right? If you want to check your answer, of course you could always differentiate this and make sure you get the integrand, what you were integrating in the first place. So if I asked you to differentiate this, by this stage everyone should know that's 3 on 2 times 2x times cos of x squared. Clean that up, that's 3x cos of x, bang, that's what I started with. Boom, done. Right? This one, when there is a power in there, don't expand, right? Unless nothing else works. Right, so this one, the 1 plus log of x, don't expand out the 1 plus log of x to the power 5. That ain't going to help. Right? You're going to end up with 6 integrals that you still can't do. Right? Each of them requiring the same substitution. Don't expand anything out unless it's just 1 plus x on its own. Say that was 1 plus x all to the 5. You know, sometimes we have to. But anything else, don't. Now hopefully this one, well, there's a log of x in there, derivative log of x is 1 on x, there's a 1 on x in there, haha, that's going to work. All right? And again, notice how I do it on the right. All right? With trig, ones involving the trig functions, we're going to do a technique that lets us handle products of sines and coses. And remember, the other 4 trig functions, tan, cosec, sec, and cot, can all be written in terms of sine and cos, right? So when you've got an integral involving the trig functions, look at the formula sheet first and see if that helps. So remember what I said, that the formula sheet, the last page of the formula sheet, this actually contains a lot of integrals, right? So the right-hand side is the integral of the central column. So the right-hand column is the integral of the centre column. The centre column is also the integral of the left-hand column. Right? So you see there's actually a lot of information in there. So this tells you, what's the integral of sec squared, the integral of cot times cosec tan. So there's a lot in there. So look here first. Right? If this isn't helping, then you try a substitution, a simple substitution like in this one here. And then if that doesn't help, we use the next method, or a method that we're going to cover next week. Right? This one, of course, we've got a root x in there. The derivative of root x is basically 1 on root x with some constants floating around, right? Those 2 root x's will cancel, give me something the formula sheet helps me with, right? So remember, we take all the integrals of the formula sheet as given, right? Let's have a look at this one. All right, now this one is x times the square root of x plus 1. The first hint is, okay, there's a square root in there that's causing me drama. Right, so I want to get rid of it. Now, initially, you would just let u equal x plus 1 and try it. Yeah? Of course, what happens here is that doesn't get rid of the x. Crap. Right? What you do then is either you try what you try first is use this use this information as a last resort if you have to. Right? So you'll notice this one's basically saying x is the same as u minus 1. So I use that, because this x didn't disappear, I use that in here to give me something that I can handle. Right? Right, so that's the thing with square roots. Now, the other thing I wanted to illustrate is, as an indefinite integral, this one, where's my pen? This one is, what is it? It's right. So as an indefinite integral, basically the way I do it, I let u equal x plus 1, solve this for dx in terms of du, then I attack the integral. The bit that prompted my attempt at my substitution. Then what you notice here is, okay, the x's haven't disappeared. Crap. Then what you do is can you use this? And yes, I can. All right, so this one implies I always turn square roots and stuff into fractional powers. Expand this out. This gives me something I can integrate. So that's 2 on 5u to the 5 on 2 minus 2/3, and then replace the u. Okay. Now, What if you're looking at that? I mean, you could check your answer by differentiating that and make sure you can get back to where you started, but everyone cheats, right? Oh, I'll just go find one of these online integrators and check my answer, right? Stop. Right, I'll go online and check my answer. What? Oh, because it listened to me. Well, about time something did. Anyway, now if you go to one of these, this is the second thing. If you want to check, just like with other things, in terms of simplifying, or I'm not really, unless I specifically ask you, that answer's fine, right? Yes, you could factor out a common factor of, right, unless I specifically ask you, I don't want you to do that. But also, as we cover all the integration strategies, we'll learn that you can do problems several ways, right? Or you might want to check your answer online, or with or on some sort of computer algebra system. And you think, all right, so here's oh, you can't see. All right, so this is a computer algebra system called Maple. It's like Mathematica. It's Mathematica's competitor, basically. Now, if I ask this to integrate, so I've got x times the square root of, right, and that's what I want to integrate. Now, if I ask Maple or any online calculator to integrate this, oh crap, that looks nothing like my answer, does it? And you think, oh shit, oh bother, I've done something wrong. Not necessarily, right? Not necessarily. So the answer we got was right, they don't look similar, do they? Right, something you could probably see, if you factor out the common factor, they are the same. Sorry? You wrote 5.2 instead of 5.2. Oh, thank you. They're the same. Right? But they don't look the same, do they? Right? And this is one of the things. If your answer doesn't look like mine, or doesn't look like something you found in another book or on one, don't necessarily assume you're wrong. Right? What Maple's doing here is it's trying it for some, which I don't really know why. These computer algebra systems will always default to integration by parts. Now you can solve this one with integration by parts, and that's where you get the first answer, which is algebraically equivalent to the second one, right? So just because your answer doesn't look like mine or look like, don't immediately assume you're wrong, right? You've just done it a different way. When we're marking your tests and things like that, I know all the different ways the answer can be written, so it's not a problem, yeah? Okay. Now the next thing last thing to do this week is something that you may have done before, but how we handle products of sines and coses. So when we've got an integral involving the trig functions, the first thing to do is look at the formula sheet and see if that's any help. If not, try a substitution, a simple substitution. If none of that is working, turn it into sines and coses and do this. Or we're going to learn a very weird technique next week to handle more complicated ones, right? Right, but this method is a way to handle just products of sines and coses, right? So there's three cases. Either sine and coses with the same argument but to different powers, right? Positive powers here, so you remember that we never use m and n are never negatives. That notation makes no sense, right? We reserve -1 for inverse. If I meant reciprocal, I'd use cosec and second cot, right, to avoid the confusion. We're going to do the case where we've got sines and coses with the same argument. So, in other words, these are both x's or 2x or whatever the hell they are, as long as they're the same. Or the cases where we've got products of different arguments. Right? So, let's say we've got an integral of this form. So, sine to some power, cos to some other power, right? Integer powers here, right? For positive integers m and n. The way we attack these depends on if m and n are even or odd, right? if either m or n or both m and n are odd, we do a trick where we peel off one of the odd powers, use the fundamental trig identity sine squared plus cos squared equals 1 somehow, and a trig substitution opposite to the one I've peeled off, and it will work. I'll show you what I mean with an example. If they're both even, this method won't work. Right? Never, ever, ever, ever use sine squared plus cos squared equals 1 to introduce a square root. You're in for a world of pain if you do that. Right? It won't work. Right? So if they're both even, peeling off one of the powers leaves something odd, the trig identity is not going to help. You want it to be even powers to make it work. Now, if they're both even, then we use the half angle formulas. Right, which half angle formula for cos says that cos of 2x is 2 cos squared x minus 1 or 1 minus 2 sine squared x. They're all of the trig properties are on the formula sheet, so you don't have to memorise them. Right? And you use that to replace the even powers as many times as you need to. Right? And remember, like all the trig identities, this says the cos of 2x, for example, the first one says sine squared is a half times 1 minus cos of 2x. This works no matter what x is. Right? So that basically says the sine squared of something is a half times 1 minus cos of 2 times that something. It always works. As long as you logically replace x, it works. And you can apply them repeatedly if necessary. And what will happen is your integral will eventually become something only involve coses, right? Coses of kx, and the integrals of cos of kx are just 1 on k sine of kx by a simple substitution. If you've got products of sine and coses that have different arguments, right, then a substitution is not going to work because they're not related, right? So what you do those is you evaluate the product form. You use the product formulas. Now, as I said, all of these are on the formula sheet. So if you go to the trig section, right, they're all here. So you don't have to memorise them. And basically for these ones, you use one of these 3. And here you just replace x and y with whatever. Because what will happen, products will become sums. That you can integrate. Right? The sums you can integrate, but the products you can't. Okay? And of course you could mix this up. If you had ones that had different powers of different arguments, you join the 2 techniques together. But as you'll discover, the algebra gets fairly hairy after a while. And there's a point where you go, screw this, right, and do it with a computer. Right? So I'm not going to give you ones that are going to be terribly awful to do. Okay? By hand anyway. All right? Now there's a couple of examples. Let me go through these with a couple of examples. Let's have a look at the first one. The first one, you've got to integrate sine squared of 3x. We look at the formula sheet first, right? And fingers crossed there's something in there involving sine squared. Unfortunately, there ain't. Crap. Right? Then you try a substitution. Well, we've got sine squared on its own. There's really nothing to... It ain't going to work, is it? There's nothing I can do. You can let u equal 3x, woohoo, you get sine squared of u, still a problem, right? It hasn't helped, right? So this is technically sine squared times cos to the power 0. Yeah, so 0 is, for our purposes, let's say it's even, right? I don't think 0 is odd or whatever, right? But you use the half angle formula. Now the half angle formula says that sine squared is a half times 1 minus cos of 2x, sine squared of x. So if I replace x with 3x, that still works, it's still true, right? So I could say that, well, that means that sine squared of 3x is a half times 1 minus cos of 2 times 3x. When I replace it, and I always take the constants outside, just don't forget to bring them along as you do the integral. So get rid of that annoying half. Now I've just got the integral of 1 minus cos of 6x. That I can do, right? If you, just like with simple chain rules, when you get the hang of it, you can do simple substitutions in your head. But if you don't want to, if you're worried, right, write it out if you need to, right? So the integral of cos of 6x is just is a sixth sine of 6x, right? And then off you go, okay? Now let's have a look at this one. I want to do this one by hand. Sine cubed times cos squared. I'll show you how this works because the what you basically do, it makes sense what you're trying to do. And let me show you how my thought process with these. All right, so we've got sine cubed times cos squared. Right, so remember, if one or both of the powers is odd, you do the peel off trick. Right? If they're both odd, it doesn't matter which one you peel off. Right? Now, only here, of course, only the sine cubed is odd. Right? So what we do here is we peel off one of the odd powers. I'll show you what I mean by peel off. Write this as right, that's the same thing, right? Or I've peeled off one of the powers. Now, the reason I put a dot there with dot shorthand for multiplication is the way this is going to work is I'm going to substitute, if I've peeled off a sine, the way I want this to work is I want to substitute u equals cos, because the derivative of cos involves sine. That will cancel with the one I've peeled off. That's the point, right? Now what I have to do is, if I've decided to peel off a sine, I want everything to the left of that dot to only involve cos. Otherwise it ain't going to work. Right? So what I do is I know that sine squared plus cos squared is 1. So what I do is I replace sine squared with 1 minus cos squared. Right? Perfectly allowed to do that. Right, now what you'll look at it, now I've got opposites to the left and the right. I've got a sine on the right and only cos is on the left. I have forced the substitution to become obvious. Right? Because if I let u equal cos, the derivative of cos involves sine, that will cancel with the one I've peeled off. And I'm sorry about the frickin' camera. All right? Piece of shit. Sorry. All right? So you do a change of variable now. Because I'm assuming if it flickers in the lecture recording too, yeah? Does it? Okay, I'll report it and hopefully get it fixed. So if I let the opposite one I peeled off, right? Derivative of cos is minus sine. Right, and the whole point is I know that that sine is going to cancel with the one I peeled off. That's the point. Right? So now I attack the integral. Right, you see how I forced the substitution to become obvious, you see? I'm going to absorb the minus 1 and expand this out. When I clean that up, that's what I end up with. Ah, that I can do. All right? I can integrate this. And then replace the u. Done. All right? So that's how these, yes? When I expand out the 1 minus u squared times u squared, I'd get u squared minus u to the 4. That's all to the right? I've left a step. You don't have to do that, right? And again, the trig ones are really notorious for if you want to check your answer, say, with an online integrator, you know, or one of these computer algebra systems or something. So if I go, oh, I don't know if that's right, I want to check my answer, right? We're integrating sine cubed oh God, what the hell did I do? You didn't do anything wrong, right? Maple's doing it by parts, which is stupid, right? Doing these ones by parts is actually a lot of work, and you wouldn't do it that way. That is actually completely equivalent to our answer, right? Because the trig functions are linked by sine squared plus cos squared equals 1, you can write this answer infinitely many ways. Now, if I replace sine squared in here with 1 minus cos squared, yep. Right? So just because your answer is different, don't immediately assume you're wrong. You know? All right, and of course, the same idea, basically this idea keeps working no matter what. As, you know, if this was, yeah, that looks bad. That answer makes it look really bad, right? But actually, what you end up with is you have to expand out. It'll become 1 minus u squared to the power 16, which you could expand out, and you know, I'm not going to be that stupid, but right, the process does keep working, right? But obviously, I'm not going to make them too high. You know, squareds, cubics, maybe order 4 if I'm being particular. That's it. I'm not going to expect you to expand a plus b to the 38. Right? Yes, I could do it. Right, but it's getting too tedious, yeah, and I'm not going to be that silly about it, right? All right, this one is cos to the 5. Technically, it's cos to the 5 times sine to the 0, right? So again, if one of them's odd, peel it off. So we write this as cos to the 4 times cos, right? Now I want everything to the left of the dot to be the opposite trig function to what's on the right. So cos to the 4 is, of course, cos squared all squared, isn't it? Replace cos squared with 1 minus sine squared, right? And when you get down to this line, you've made the substitution obvious. If I let u equal sine, its derivative involves cos, which is going to cancel with this one, done. Right? And so you end up with a 1 minus u squared all squared, right? Which I can expand out and integrate. Right? So it keeps working. If they're both even, if they're both odd, it won't matter which one you peel off, but peel off the higher one, right? Because the lower one will be the one that you've got, will replace with 1 minus u squared to some power. Saves your work, right? Again, that's a skill that you'll develop as you get practice. Okay, so that's how we handle ones where they're products of sines and coses of the same argument. When they're different arguments, this ain't going to work, right? Because these two trig functions, sine of 4x and cos of 5x, are not related, right? Please don't make the mistake that it's, you know, sine of 4x is 4 sine of x. The trig don't work that way, right? So no substitution or anything's going to work because the derivative of one's got nothing to do with the other one, right? If this was sine times cos, if this was sine of x times cos of x, easy, right? Because the derivative of cos is sine, I can let u equal cos, or the derivative of sine is cos, I can let u equal sine. This one, it ain't going to work, right? And you know, I say this not to be funny because I have seen this. All right? Don't do crap like that. All right? It doesn't work that way. All right? Nor does this thing equal, or does it equal, you know, no. All right? That don't work. All right? Think back to these things are right-angled triangles. A triangle with an angle 4x and a triangle with angle 5x are not frickin' related. All right? This stuff doesn't work. So this one, what we do here is, because the way it's currently written, there's nothing I can do with it. So what I do is I use the trig properties to help me, right? And I'm going to use this result. Sine A times cos B, and remember this is on the formula, you don't have to memorise this. I mean, I swear, one of the main reasons I'm such a big thing with why I give formula sheets is because I could never remember these in school, ever. I was useless. My memory's terrible, right? And I'd always stuff up which one's plus, which, you know. And so whenever I needed these in a test, I'd prove them, right? Which is a waste of freaking time, right? To make sure I got the right sign and things like that. So, one of the reasons I'm a big believer in formula sheets is because the amount of time I wasted proving this rubbish, I swear to God, I've proved this result 50,000 times and I still don't remember it, right? So now I look it up, right? And that's why I do formula sheets. And also remember that A and B can be anything, right? Doesn't matter what they are. So replace A with 4x, B with 5x, it still works. The only extra thing to remember is that sine is odd and cos is even. So the sine of minus x becomes minus sine of x. Right? Now you've got something you can't integrate, you've broken it into two things you can. Right? The first one's a simple substitution. Do the substitution if you need to. The second one, straight off the formula sheet. Okay? Right, and off you go. Now, as I said, you can join these two things together, but I'm not going to be that mean about it. What I mean, for example, is I could ask you, you could join these two methods together. Let's say I asked you, not that I would be this cruel, now how would you attack that one? Right? This is actually, to do this by hand is a lot of work. Right? What you would do is I would have to replace, how would I do it actually? I'd peel off one of the signs. What I would do, not that I'm going to, but what I would do, how would you do this one? So let's say we've asked, this is not one I'm going to ask you to do, right? But let's say I decided that you're all annoying the hell out of me, and I decided to give you a monster question. Right. Join these two methods together, right? Now, the way I would do this is then I would say then use the product formula for the bit in there, expand it out. You're going to have sines or more products of sines. Apply the product formula, all of those, expand all of those out, and you'll keep going and going and going until everything just involves sine of 2x. Right? It'll be about this long. Then you'd integrate it. Right? But you could do it, but it becomes a point where it just gets ridiculous. Right? So to show you, I ain't going to get you to do that. Right? Right, but you could, right? So I'll either give you ones that have sine and cos of the same argument to different powers, or sine and cos to the power 1 with different arguments. Yes, in theory you could join the two methods together, but it just becomes too tedious to do it by hand. I mean, as long as you, I'm happy to use a computer algebra system because I think, yes, I could do that by hand, but I don't want to. Right? But you could, as long as you do understand what the computer is doing. Right? That's the whole point of studying this stuff. That yes, we can use computers to help us, but it is important at university, especially, to actually that you understand what it's doing. Right? And I say this one would be awful to do. Right? So I won't give you ones like these. I won't mix them together. Right? And if I was going to mix them together, I'd give you a lot of hints about it along the way. Okay. Right, but basically, that's how we handle. So these are just trig substitutions, although the only time you do a substitution is if one or both of them are odd. So when they're both even, you're only doing very simple substitutions to integrate the causes of kx's, and the same here. Right? So that lets us handle the trig one. So the main thing are, when you've got integral involving trig functions, You look at the formula sheet first and hope it helps. Most likely it won't, right? But it might. You might get lucky, right? I might have slept up. Try a simple substitution. If that's not working, turn everything into sine and causes and do this, right? Something's got to work, right? I won't give you ones that won't work, okay? All right, so please make sure you do practice all of these examples because this will help. The first method we do next week, what we're going to do is turn integrals into trig integrals. So it's important that you can do the trig ones first. So please make sure you practice these ones, right? And I'll see everyone next week for when we'll continue with the integration strategies. All right, thanks everyone. Yes. Oh, hang on. Let me turn this off. Hang on.
Okay.